Good day, dear friends. Hope this finds you fit and fine. I'm Pranasish. I am back here to give you ideas about circular motion, angular displacement, instantaneous angular velocity, instantaneous angular acceleration, and their relationships with their linear counterparts. These are the very useful expressions we find while analyzing the curvilinear motion of a particle. And I'm quite sure the knowledge you gain from this video will just be superficial unless you have gone through exactly the last three videos in which these expressions were beautifully deduced with detailed explanation. I'm going to introduce another unit vector to you. Unit binormal. An unit binormal is the vector product of the unit tangent and the unit normal. Thus we write vector B is equal to vector T cross vector N, and the unit tangent, the unit normal and the unit binormal are all mutually perpendicular to each other. So we can write vector T is equal to vector N cross vector B. The magnitude of the instantaneous linear velocity is equal to V is equal to S dot. Now, let me mention some vectors: angular displacement, angular velocity, angular acceleration, angular momentum, torque, the moment of a force, the moment of a couple, the angular impulse, and all these vectors are axial and they are directed along the axis of rotation or along the unit binormal. And the specific direction can be obtained by right hand thumb rule. Let a particle move along this circular path of radius r, not r, rho. The radius vector is directed radially outward, but the unit normal is directed radially inward. So we can write the radius vector is equal to negative the magnitude of the radius vector multiplied by the unit normal. Let the particle move from point A to point B. The length of arc AB is S. So the distance the particle travels is S. Arc AB subtends an angle theta at the center of curvature or the center of the circular path. The angular displacement of the particle has magnitude of angle theta, and the angular displacement is an axial vector, so it is directed along the binormal. So we write the angular displacement vector theta is equal to theta binormal. Now let's find the relationship between the linear displacement and the angular displacement. From this expression we can write d vector r is equal to ds unit tangent is equal to, in place of s we can write, from here you see that s equal to rho theta when theta is expressed in radian unit. Then in place of s we can write rho theta unit tangent is equal to, rho is a constant, so rho d theta. In place of unit tangent we can write vector n cross vector v is equal to, we can write rho vector n cross d theta vector b. Now let's exchange the positions of these two vectors. So we write d theta vector v, but we have to give a negative sign, and we put the negative sign here. In place of d theta vector v we write d vector theta cross, in place of minus rho vector n we write vector rho. And this is the relationship between the linear displacement and the angular displacement. The angular velocity vector omega is defined as the instantaneous rate of change of the angular position with respect to time. So d vector theta dt. And angular velocity is also an axial vector, and it is directed along the binormal. So we write vector omega is equal to omega vector v. Now let's find the relationship between the instantaneous linear velocity and the instantaneous angular velocity. Let's divide both sides of this equation by dt. We get d vector r dt is equal to d vector theta dt cross vector rho. Here we write vector v is equal to, here we write vector omega cross vector rho, and this is the relationship between the instantaneous velocity and the instantaneous linear velocity and the instantaneous angular velocity. And the instantaneous linear velocity is equal to the instantaneous angular velocity cross the radius vector. Now let's find the definition of instantaneous angular acceleration, and it's given by vector alpha is equal to the instantaneous rate of change of the angular velocity with respect to time. Thus we write d vector omega dt, and it's also an axial vector, so we write vector alpha is equal to alpha unit binormal. Now let's find the relationship between the instantaneous linear acceleration and the instantaneous angular acceleration. Vector A, instantaneous linear acceleration, is equal to s double dot vector t plus s dot squared divided by rho vector n. In place of s double dot we write d s dot dt vector t plus s dot squared divided by rho vector n. Is equal to, in place of s dot we write v, so dv dt In place of vector t, we write vector n cross vector b plus s dot squared divided by rho vector n is equal to, in place of v, we write omega rho vector n cross vector v plus s dot squared divided by rho vector n. From this relation, we see that all these vectors are mutually perpendicular to each other, and so scalarly we can write v is equal to omega rho. Here rho is constant, so rho d omega dt vector n cross vector b plus s dot squared divided by rho vector n is equal to rho, in place of d omega dt, we can write alpha vector n cross vector v plus s dot squared divided by rho vector n is equal to rho vector n cross alpha vector b plus s dot squared divided by rho vector n is equal to, now let's exchange the positions of these two vectors. Alpha vector b cross negative rho vector n plus s dot squared divided by rho vector n is equal to, in place of alpha vector b, we write vector alpha, and in place of minus rho vector n, we write vector rho plus s dot squared divided by rho vector n, and this is the relationship between the linear acceleration and the angular acceleration. And thus we find the expressions and the definitions of angular displacement, instantaneous angular velocity, instantaneous angular acceleration, and their relationships with their linear counterparts. Thank you, and wait for the next video. It will be more interesting. Have a good day.